Good morning everyone. My name is Muskan Kumari and my roll number is 205008. Today I am going to give presentation on the topics groups and subgroups. So before discussing groups and subgroups, let us know about some terms which will be helpful in the discussion of groups and subgroups. So the first term is binary operation. So what is a binary operation? Suppose G is a non-empty set. Any map f G cross G to G is called binary operation on G or binary composition in G. Thus, an operation which combines two elements of a set to give another element of the same set is called a binary operation or binary composition. So, the second term is algebraic structure. A non-empty set together with one or more than one binary operation is called an algebraic structure. Example, set of real numbers having plus and under plus and multiplication operation is an algebraic structure. So coming on to group, what is a group? So let S be a set and star be an operation defined on set S. Then S is called group for operation star if the following conditions are satisfied. The first condition is S is closed for the operation star. Second condition is associativity hold in S for the operation star. Third condition is identity element for the operation star exists and belong to S. And the fourth condition is inverses of every element of S exist and belong to S. Now we will discuss an example of group. So in this example we have to prove that the set G equals to 0, 1, 2, 3, 4 under addition modulo 5 is a finite group. As we can see, this set is finite as it has finite number of terms. So let us prepare the composition table for this set. So as we can see, when 0 is operated over 0, we'll get 0. When 0 is operated over 1, we'll get 1. When 0 is operated over 2, we'll get 2. When 0 is operated over 3, we'll get 3 and so on. So this is the composition table. As we can see that in this composition table, every element that belongs to this also belongs to set G. It means there is no foreign element in the composition table. So closure property holds here. Now the second property is associativity. Associativity also holds for the addition modulo 5. So associative law also satisfies here. Coming on to the third property, that is existence of identity. So here 0 is the identity element as 0 plus 1 equals to 1 plus 0 equals to 1. 0 plus 2 equals to 2 plus 0 equals to 2. 0 plus 3 equals to 3 plus 0 equals to 3. 0 plus 4 equals to 4 plus 0 equals to 4. Now coming on to the fourth property, that is existence of inverse. So here inverse of 0 is 0 itself. Inverse of 1 is 4. Inverse of 2 is 3. And inverse of 3 is 2. And inverse of 4 is 1. So here inverse of every element of G exists. So G is a group under addition modulo 5. One thing which is to be noted here is that in this composition table, commutative law holds as the corresponding rows and columns in the table are identical. So such groups in which commutative law also holds in addition to other conditions which are needed to be satisfied so that a set is called a group. In addition to that, if commutative law also holds, then the group is called abelian group. Now coming on to the subgroups. So before discussing subgroups, let us discuss about the properties which are transferred from a group to its subset. So if G is a group, It will have closure property, associativity, existence of identity, existence of inverse, and commutativity if the group is abelian. So the closure property is not always transferred to the subset. Associativity is always transferred to the subset. Identity, existence of identity is not always transferred to the subset. Existence of inverse is also not always transferred to the subset. And if the group is abelian, commutativity is transferred to the subset. So the properties which are transferred from group to its subset are called inherited properties. These are inherited from set to subset or group to subset. Okay, so let G be a group. Now coming on to the subgroup. What is subgroup? So if G be a group for the operation star and let S be a subset of G, then S is also called subgroup of G if S star is also a group. Now we'll understand what is subgroup using this example. In this we have to prove that the additive group of even integers is a subgroup of all integers under addition operation. So we are given that the set of integers is a group, that is 0 plus minus 1 plus minus 2 is the set of integers and it is a group. We know it is a group. And its subset is set of even integers, that is 0 plus minus 2 plus minus 4 plus minus 6 etc. We have to prove that H is subgroup of G. For that H should satisfy two conditions. Firstly, it should be the subset of G, which it is, and secondly, it should follow all the conditions, or it should satisfy all the conditions of a group. Coming on to the first property, that is closure property. As the sum of two even integers is always even, that's why here closure property exists. Associativity is inherited from G, as H is the subset of G, so associativity is inherited from G to H. Third is existence of identity, as here 0 belongs to H and 0 is the additive identity, as 0 plus A equals to A plus 0 equals to A. So the fourth property is existence of inverse. Here inverse of every element exists. As you can see, inverse of 2 plus 2 is minus 2, it also exists here. Inverse of plus 4 is minus 4, it also exists here. Inverse of minus 6 is plus 6, it also